Hello everybody, welcome to the Ultimate Physics channel. The topic of this video is cavity radiation, blackbody spectrum, Rayleigh-Jeans law and its derivation. Before we venture into a detailed discussion of the topic of this video, it is important that we understand a few fundamental ideas regarding this topic. First, we have to understand what is thermal radiation and what is a black body. Then we can proceed on to discuss the topic of this video. What is thermal radiation? All objects above absolute zero temperature, that is 0 Kelvin, emit radiation, which is basically electromagnetic radiation, typically in the invisible infrared range of the spectrum that is generally not visible to us. So the radiation emitted by objects because of their temperature is called thermal radiation. The rate of emission exceeds the rate of absorption generally as long as the thermal equilibrium is not attained. Once the thermal equilibrium is reached, the rate of emission and the rate of absorption become equal. Generally, objects that are good absorbers of thermal radiation are also good emitters. But there is one class of objects that are very good absorbers of thermal radiation. They absorb all radiation that is incident upon them. Such objects are called as blackbodies. So blackbodies absorb all radiation that is incident upon them. Two types of objects can be given as examples for blackbodies. The first example would be an object that is coated with a diffuse layer of black pigment such as lamp black or bismuth black. Objects generally appear to us because of the light they reflect. But objects can also be visible to us when they start emitting light, that is, when they are self-luminous. But self-luminous objects are generally at high temperatures. So at ordinary temperatures, for an object to be visible to us, it has to reflect light. But an object that is coated with a black pigment does not reflect any light and therefore they do not appear to us, but such objects are black bodies because they absorb all radiation that is incident upon them. Now there is a second class of objects that are black bodies. They are objects that contain a cavity which is connected to the outside world through a small hole. The second class of objects that can be called as black bodies are objects that contain a cavity, such as the one shown here, which is connected to the outside world through a small hole. Now, the surface of this hole allows a small amount of radiation to pass through to this cavity, and the radiation that enters this cavity undergoes multiple reflection before getting completely absorbed. Now, this hole therefore absorbs all radiation that is incident upon it and only lets out a small fraction of the radiation from inside to the outside world. So the surface of the hole behaves like a true black body. Any radiation that is generated within this cavity, a small fraction of that can go to the outside world, and therefore this object does not allow radiation to escape from its surface, thereby acting as a black body. Most experiments that involve studying the spectrum of black bodies in laboratories are constructed along these lines. They are useful in studying the black body radiation, and they were useful in developing a classical theory of black body radiation such as the Rayleigh-Jeans law. Because of the importance of such cavities as black bodies, it is important to discuss these objects in some detail to understand the connection between the cavity radiation and the black body spectrum. Any radiation that is incident upon this hole enters through the hole into the cavity and gets reflected multiple times before getting completely absorbed by the cavity. Therefore, the surface of the hole behaves like a black body in absorbing all radiation that is incident upon them, and only a small fraction is allowed to escape through this hole. When the cavity is heated to temperature T, electromagnetic radiation belonging to the thermal range of frequencies is generated within this cavity, and any radiation that is incident upon the surface of the hole from the inside comes out through this cavity in the reverse process And this radiation is typically a black body radiation because the surface of the hole behaves like a black body. We have already seen that. Now, the area of this hole is very small compared to the inner surface area of the cavity, and therefore the radiation that comes out from this hole is a small sampling of the radiation that is contained within this cavity, and therefore the radiation that is contained within this cavity also must be black body radiation because this surface behaves like a black body, the whole surface. Therefore, we have established that the radiation present within the cavity is black body radiation, and therefore the spectrum that is obtained on the radiation that escapes through this cavity is a black body spectrum. So if we analyze that spectrum, that would have a typical shape of black body spectrum, which is basically this. So if you plot, let us say, energy density here for a given temperature of the black body as a function of frequency, we get a spectrum of this kind, which is a typical black body spectrum. Thus, the hole behaves like a true black body, and this is the link between the cavity radiation and the black body spectrum. Since we have established the link between cavity radiation and black body spectrum, let us proceed to discuss the Rayleigh-Jeans law in some detail. Shortly after the turn of the 20th century, Rayleigh and also Jeans calculated the energy density of the cavity radiation or black body radiation that pointed up to serious conflict between the classical theory and the experimental results. Let us first generally outline the strategy employed by Rayleigh and Jeans in their calculation of energy density, and then go on to do the actual derivation of the Rayleigh-Jeans law. Consider a cavity with metallic walls that are heated to temperature T. Now, the radiation that is produced within this cavity is electromagnetic in nature because the charges present in the walls of the cavity, because of thermal agitation, radiate electromagnetic waves. It is not important to study the details of the electrons present in the walls in detail, but it is important to understand the electromagnetic waves that are produced in the cavity in order to study the black body spectrum. Rayleigh and Jeans proceeded as follows. First, classical electromagnetic theory is used to establish that the waves that are produced within the cavity are standing waves with nodes at the walls of the cavity. Then, by using geometrical arguments, a count of the number of waves in a given frequency range, let us say nu and nu plus d nu is made. And once this number is calculated, it is possible by using the classical kinetic theory to obtain the average kinetic energy of entities of similar kind present in a system, which is basically kT, and then therefore by multiplying the number of waves present in a given frequency range by the average energy of these waves and dividing the whole thing by volume of the cavity, one can get the energy density of the cavity. This was the strategy employed by Rayleigh and Jeans in their calculation, and therefore let us proceed to do that in our derivation as well. For simplicity, we have taken a cavity which is in cubical shape with edge length A that is filled with electromagnetic radiation. Standing waves are formed between each of the three pairs of walls corresponding to the x, y and z directions of this cavity. The radiation that is reflecting back and forth between these walls can be analyzed into three components along these three directions. Since the opposing walls are parallel to each other, these radiations can be studied independently and they do not mix. Consider first any radiation that is incident on the back wall, that is at x is equal to 0. Now this radiation gets reflected back and forth between these two parallel walls and form standing waves. Now at x is equal to 0, the radiation is propagating perpendicular to the wall at x is equal to 0. So in an electromagnetic radiation, the electric field vector is perpendicular to the propagation direction, and therefore the electric field vector in this case must be parallel to the wall at x is equal to 0. A metallic wall, however, cannot support a parallel electric field because charges can always flow in such a way as to neutralize the electric field. This we know from fundamental electromagnetic theory. Therefore, we know that electric field is 0 at the wall at x is equal to 0. And since this electromagnetic wave is reflecting back and forth between walls at x is equal to 0 and x is equal to a, because the edge length of this cavity, cubical cavity, is a, no electric field can be supported by the wall at x is equal to a as well. Therefore, the electric field vanishes at these two walls at x is equal to 0 and x is equal to a, and therefore the x component of the electromagnetic wave vanishes at x equal to 0 and x equal to a, and thereby proving that a standing wave nodes occur at these two walls. For the same reason, one can argue that the walls at y is equal to 0 and y is equal to a, as well as the wall at z is equal to 0 and z is equal to a, they also form standing waves at the walls. So the three components of this electric field of the electromagnetic wave, namely the x, y and z components, they form standing waves at the three pairs of walls of this cubical cavity. These conditions put a limitation on the number of possible wavelengths and thereby number of possible frequencies that are allowed for the electromagnetic radiation present in this cavity. Now we shall consider the question of counting the number of waves present within this cavity in a frequency range nu and nu plus d nu, or equivalently lambda in terms of wavelength, lambda and lambda plus d lambda. In order to calculate the number of waves present in the given frequency or wavelength range, let us first do the calculation for an artificial case of one-dimensional cavity, that is only for the x component of the electromagnetic radiation alone, and later extend it to the three-dimensional cavity or all the three components of the electromagnetic radiation. The electric field for the one-dimensional electromagnetic wave can be mathematically described by using the function E of x comma t is equal to E naught sine 2 pi x over lambda multiplied by sine of 2 pi mu t, where E of xt is the electric field of the electromagnetic wave, that is, it is a function that describes the electric field of the electromagnetic wave. E naught is the maximum amplitude of this electromagnetic wave. Sine 2 pi x over lambda captures the spatial variation of the electric field of the electromagnetic wave, and sine 2 pi nu t captures the temporal variation of the electric field of the electromagnetic wave. Lambda and nu are wavelength and frequency respectively, and they are linked by the relation C is equal to nu times lambda, where C is the speed of the electromagnetic wave. So we can clearly see this, that the electromagnetic wave oscillates sinusoidally both spatially as well as temporally. Now, when we say that the wave forms nodes at the walls of the cavity, that is, in order for standing waves to be formed, we need nodes at both the ends of this cavity, that is, at both the walls. Let's say in the x direction at x is equal to 0 and x is equal to a. That means the electric field vanishes at those 2 points, which you already established, and that means the electric field E of xt must go to 0. Under what condition E of xt will go to 0? We can clearly see that this cannot be 0 for a given wave, and this part is not going to be 0, but only this part can be made to be 0. That is, if this particular part has to be going to 0, that is sine of 2 pi x by over lambda must be going to 0. This will happen only for sine, if this particular thing is, let us say, sine n pi is generally 0 in our sinusoidal wave. It repeats after every pi, 0, pi, 2 pi, and so on. Right? This is the general behavior of any sinusoidal function, and therefore sine n pi is equal to 0. That means this has to be linked to 2x over lambda must be equal to n. So this implies that the condition 2x over lambda is equal to 0, 1, 2, 3, and so on, those positions of x that satisfy this condition, the wave has fixed nodes. In order to satisfy the condition that the wave has fixed nodes at both ends of the cavity, let us fix the origin at x is equal to 0 for this particular axis, so that at x is equal to a, 2x by lambda is equal to n, where n is now 1, 2, 3, and so on and so on, that x is equal to a. And therefore, this would mean that we have a condition 2a over lambda is equal to n. That is a condition. That condition provides us the allowed wavelengths for this particular cavity. These are the allowed wavelengths for this particular cavity, where n is the integer 1, 2, 3, and so on and so forth. We have obtained the condition 2a over lambda is equal to n, and in terms of frequency, lambda is equal to c over nu. Using this here, we can say 2a over c times nu, the frequency is n, or in terms of frequency, if you want the conditions, we say that n times c over 2a is the condition. So these are the allowed frequencies for the electromagnetic wave that is to be present in the cavity. Now this can be easily represented. These are the different modes of the wave, so to say. So we can easily represent that as for n is equal to 1, this is the mode, and then for n is equal to 2, this is a 1. For n is equal to 3, this is the 1. Right? These are different modes, for example. So here we know that the condition n is equal to 1, 2, 3, and so on and so forth. We can keep kind of drawing. The wave patterns for these different ends here. So these are the amplitude patterns for the standing waves formed within the cubical cavity. So these are the allowed values of frequencies or wavelengths for the cavity, and we can represent this by using a diagram in which we plot along an n-axis the integer values n is equal to 1, 2, 3, and so on and so forth, and then the number of waves can be calculated by counting the number of points along this axis for a given distance. So in that distance, how many points are there, that would correspondingly convert into the number of waves that can be present. So let us do that. This is the n-axis in which we draw points at various allowed values of n on this axis, starting from 0, 1, 2, 3, 4, 5, and so on and so forth. And for any given distance, the number of allowed waves would just be a count of the n on the n-axis. And therefore, let me say that based on our equation for the wavelength or for the frequency, c by 2a times n, we can say that on this axis d is equal to 2a by c mu. That is the reverse of this, because the n is corresponding to the distance here on the n-axis, and let us say that is up to a particular distance d. For another distance d here, let us say the n would correspond there to be 2a c mu plus du. This is another small distance, additional distance, let's say here. In terms of frequencies, this would be the case. And therefore, the difference here, that is the number of waves that can be present in a frequency range nu and nu plus du, would be a difference of these two, and that would be 2a over c times du only. So if we call that as, let's say, some number of frequencies in a range n nu du as a function, that would be 2a over c du. And it is interesting to note here that the number of waves in a given frequency range does not depend on the frequency itself in this one-dimensional case. Rather, it depends just on the range, that is the difference in frequencies that we want to see, the difference, the range within which we want to count the number of waves. That is important to note that. In the 1D case, this is true. Now, this would be actually not the exact number, because in an electromagnetic wave, there are two independent states of polarization. Therefore, we have to multiply this result by 2 to get the actual number. So, the actual number of waves that are allowed in a one-dimensional case cavity is this. So, this is the actual number of waves that are there. So we have been able to count number of waves in a given range of frequencies between nu and nu plus du nu, say, as this particular expression. Now we have established a procedure for calculating the number of waves in a given frequency range for a given cavity. And this procedure can be extended to a three-dimensional cavity to calculate how many number of waves are present in a three-dimensional cavity, which is a real case in a given frequency range between nu and nu plus du. So let us proceed to do that calculation, and finally that would lead us to the Rayleigh-Jeans law derivation. In order to extend the calculation that we perform for the one-dimensional case to a three-dimensional case, we have drawn a diagram here where we have taken three mutually perpendicular axes nx, ny and nz, where all these three axes basically correspond to our n-axis in the one-dimensional case. So we have replaced the single axis n-axis with the three axes here which are mutually perpendicular, and any point along these three axes corresponds to allowed values of n along that particular axis, and therefore any combination of nx, ny and nz would lead us to the allowed frequencies, the number of allowed frequencies or wavelengths in this case. Each point on this array represents an allowed value of the standing wave. This procedure is equivalent to analyzing a three-dimensional wave that is propagating in some arbitrary direction, let us say r here, into three different components and analyzing them independently. Here the number of allowed frequencies can be calculated by counting the number of points in this three-dimensional space that would exist between the shell at R and the shell at R plus dr. If that thickness, how many number of points are present in this three-dimensional space, that tells us the number of allowed frequencies for our standing waves. Let us proceed to do this calculation now. We have drawn a diagram here to represent an electromagnetic wave propagating in an arbitrary direction within the cavity, and we have shown planes at those points where nodes are formed for the standing wave. We know that nodes are formed at every half wavelength, that is in the three directions, lambda x by 2, lambda y by 2 and lambda z by 2, and then the next node is at lambda x, lambda y, lambda z, and then next three halves of the lambdas in each of these three directions, namely 3 lambda x by 2, 3 lambda y by 2, 3 lambda z by 2, and so on and so forth. We can keep representing them in parallel planes to understand the positions at which nodes are formed for a wave that is propagating in an arbitrary direction in three-dimensional space. We can write some conditions here because the direction of the propagation of this wave is decided by the angles that it forms from the origin with respect to the three axes x, y, z and z as alpha, beta and gamma. These are the angles that this particular direction of propagation of this electromagnetic wave forms with respect to the three axes, and therefore we can write straight away some relations based on the angles. So lambda x by 2, for example, the first plane is at lambda x by 2. For that it is actually lambda x by 2, and that would correspond to for the wavelength of this wave lambda, let us say 2 cos alpha. That is because alpha is the angle that it forms with the x direction. Lambda y over 2 is lambda over 2 cos beta, and lambda z over 2 is equal to lambda over 2 cos gamma. These are the three expressions that we begin our discussion with. Now we can proceed to write the electric field functions for this electromagnetic wave for each of the three components along the x, y and z directions, namely E x comma t is equal to E naught x now sine 2 pi x over lambda x sine 2 pi nu t. These are the three expressions for the electric fields corresponding to the three directions x, y and z. We can see clearly that the temporal part of this function does not change for the three components, whereas the spatial parts along the x, y and z directions, that changes. And here lambda x, we have relations here, so we could. From our earlier discussion, we know that it is this spatial part that has to go to 0 in order for this electric field to vanish at the node points, and therefore for that to occur, we know that the condition for that is 2x over lambda x, in this case for the x component, has to be 0, 1, 2, 3 and so on and so forth. And similarly we can write 2y over lambda y is equal to, and then 2z over lambda z is equal to. So these are the general conditions for these three components to vanish for forming standing waves with the nodes at those points, satisfying these three conditions. Now if we keep x is equal to 0 as the origin where the first node is formed, then we know that there is a node on the axis, the corresponding axis at a point x is equal to a, let us say. For that, we can write the condition as 2x over lambda x is equal to nx, and 2z over lambda z is equal to nz. We know that lambda x is equal to lambda over cos alpha, lambda y is equal to lambda over cos beta, and lambda z is equal to lambda over cos gamma. Now using these three expressions here, we can write 2x over lambda cos alpha is equal to nx, 2x over lambda cos beta is equal to ny, 2x over lambda cos gamma is equal to nz, and x is equal to a, where there is definitely a node, we can write 2a instead of x there over lambda cos, right? And if we square and add the left hand side and the right hand side, we would end up with an expression where 2a over lambda whole squared, because we have squared it, cos squared alpha plus cos squared beta plus cos squared gamma is equal to nx squared plus ny squared plus nc squared. We note that this term goes to 1, right? So the remaining is 2a over lambda squared is equal to nx squared plus ny squared plus nz squared. Or 2a over lambda alone is equal to square root of nx squared plus ny squared plus nz squared. Please recall that from our earlier discussion of the three-dimensional wave propagating in an arbitrary direction, the length was r. So here in this case, therefore, our 2a over lambda would correspond to therefore r. And from here we can continue over here. That would be 2a by c times nu would be r, and therefore nu is equal to c over 2a times r. This equivalency is because of our construction where we have taken nx and ny and nz to be the three axes to account for the number of allowed waves along three directions x, y and z, and therefore this relation holds true. So in our diagram, let us say nr is the number of lattice points present between the two shells of radii r and r plus dr, and then dr is the thickness of the shell itself. That means nr dr is the product of the density of lattice points to the volume of the shell itself, and that would correspond to, because it's an octant of a sphere, that would correspond to 1/8 of the surface area of that spherical shell multiplied by its thickness dr, and this would be simply equal to pi over 2 r squared dr. nr dr. And since the entire construction is to count the number of frequencies, NRDR would be equal to N nu d nu, and therefore R and nu are connected by this relationship. So therefore d nu from this is the constant C over 2A times dr, and R squared would be from here 2A over C whole square, and nu square. So here d nu we can convert into dr by writing it as dr is equal to 2A over C d nu. So we can substitute pi over 2 times r square 2A over C whole square, and there is another 2A over C here, so whole cube, then u square du. So this gives us the number of waves in a given volume in three-dimensional space, and here we can do refinement of this particular expression. Sorry, this is new now, okay, is equal to expand this one, you get 4, because this is 8 pi over 2, that is 4 pi a cube over c cube nu squared d nu, and particular expression has to be multiplied by a factor of 2 to account for the two states of polarization of an electromagnetic wave, and therefore our n nu d nu would be equal to 8 pi a cube nu squared d nu over c cube. If the volume of the cavity is a cube, then because we have taken a cubical cavity, let's say, then our n nu d nu is equal to 8 pi, we have divided here by volume, let us say, then we have 8 pi nu squared d nu over c cube. So this gives us the number of modes or number of waves in a given frequency range between nu and nu plus d nu per unit volume, because we have divided here by volume to get rid of the a cube. Now we have to calculate the energy density of the electromagnetic wave in the cavity, and that can be done by multiplying this with the average energy of the system of waves in the cavity. It is important to note that the number of waves for a given frequency range nu and nu plus d nu depends here on nu squared. In the one-dimensional case, it was independent of the frequency, it was only dependent on d nu. Whereas in the three-dimensional case, which is the real case, it also depends on the frequency nu squared. That means the dependency on frequency is the number of dimensions minus 1, or 1 less than the number of dimensions is the power that goes to the frequency. That is the dependency of the number of waves in this case, and this has been generally assumed to be true. Because we live in a three-dimensional space, this happens to be nu squared, and that is interesting to note here. Now to calculate the energy density, which was actual calculation performed by Rayleigh-Jeans, we have to multiply this by the average energy of a system in thermal equilibrium containing a a large number of similar entities. Using classical kinetic theory, Rayleigh and Jeans were able to prove that average energy is equal to kT. The next step in the calculation of the energy density in the Rayleigh-Jeans derivation is the average energy of each of the standing wave in the cavity of frequency nu. Now, classical kinetic theory says that in a system having similar entities, a large number of similar entities in thermal equilibrium, the average energy is given by the expression now any particular wave in this cavity, we know that the energy of the particular wave can be any value from 0 to infinity. But when we consider the whole system of waves, these waves are similar entities in thermal equilibrium within the system. That means these waves can exchange energy with each other, and therefore they are subjected to the laws of the kinetic theory. The classical kinetic theory makes a very definite prediction about the average energy of such entities in thermal equilibrium. We can apply this argument to our case because our system consists of a large number of standing waves which are similar entities, and they are at a particular temperature T, which is the temperature defined for the wall of the cavity. Thermal equilibrium is ensured in our case because the walls of any real cavity will constantly absorb and re-radiate radiation, thereby ensuring exchange of energies with the entities present in the cavity, which are the waves in our case, and therefore this exchange of energy ensures that thermal equilibrium will be eventually attained by the system, and therefore we can apply the classical kinetic theory arguments to this case as well. The prediction of this average energy of such a system in thermal equilibrium comes from what is called as the law of equipartition of energy. According to this law of equipartition of energy, for a system containing a large number of similar entities in thermal equilibrium, the average kinetic energy of the system is half kT where this 1 here comes from the number of degrees of freedom present in that system. In our electromagnetic waves, in the case of our electromagnetic waves, the only degree of freedom is the amplitude of the wave that is allowed to change, and therefore this can be applied to our case. In fact, the law of equipartition of energy states that for a system containing n gas molecules, the average kinetic energy of the system is half kT per degree of freedom, where K is the Boltzmann constant given by and in such systems where the average kinetic energy is half kT, the total energy is twice the kinetic energy, because for systems containing 1 degree of freedom, the total energy is twice the average kinetic energy. For example, even in the case of a pendulum or a spring, there is only 1 degree of freedom there, and the law of equipartition predicts that that average energy is kT. And therefore, we can apply this to a system of standing waves and say that the average energy, total energy rather, is going to be equal to kT. Thus, each standing wave in the cavity, according to law of equipartition of energy, has an average energy of kT. And therefore, this particular expression can be used in our calculation for the energy density of the standing waves in the cavity. Let us proceed to do that. We need energy density of waves at a particular temperature in a particular frequency range nu and nu plus d nu, and that is the number of waves per unit volume, number of waves per unit volume in a given frequency range multiplied by average energy per wave, right? So we know that from our earlier discussion, the number of waves per unit volume we calculated as 8 pi nu squared d nu over c cube. And this one, if we multiply with kT now, we get what is called as the expression for Rayleigh-Jeans law. That is 8 pi nu squared kT, let us say, over c cube d nu. So this is the final expression for the Rayleigh-Jeans law. So that completes our derivation of the Rayleigh-Jeans law. But what is its interpretation? Right? The observed blackbody spectrum has a pattern of this kind. So with increasing frequencies, the energy density that is experimentally obtained has a spectrum of this kind. But if you plot this particular expression arising from the Rayleigh-Jeans law, you will get something like this. So there is a deviation after the initial range of frequencies. Initially this goes pretty close to this one, and then there is a deviation, right? This is the prediction of the Rayleigh-Jeans law, whereas this is experimental. So there is a deviation at higher frequencies, and there is a discrepancy or disagreement between the theoretical prediction and the experimental results, and this deviation at higher frequencies was famously called as the ultraviolet catastrophe. So this was a major problem with the classical theory, which Rayleigh-Jeans law is, of course, and therefore that led Max Planck to work on this problem, and that led to the birth of quantum mechanics. That brings us to the conclusion of this video. Hope to catch up with you soon on another interesting video. Until then, it's bye.